Hello, grade 12. Welcome back to the channel. We are back once again with vertical projectile motion. And in this session, I'll be teaching you how to draw and interpret VPM graphs. So before we start with the lesson, please like, share, and subscribe to the channel so that you get more of this content. Without any further ado, let's just get right down to the lesson. So now we know when it comes to graph, we have three types of graph. We have the velocity versus time graph, the position versus time graph, and the acceleration versus time graph. So in this lesson, we'll be going in depth with each and every type of graph here and just looking at different scenarios and how we draw this graph in those different scenarios. So on this one, you need to understand that when it comes to the velocity versus time graph, when we have downward is positive, we understand that our acceleration will be positive 9.8 meters per second square. But then the graph here will be an increasing function, right? So if we have downward as positive, note that the graph will start from down below here and go all the way up, so becoming an increasing function. So the idea here is if we have downward as positive, remember, if your graph is above, if your graph crosses the x-axis, that indicates a change in direction. So when the graph passes this x-axis and goes upward, we are saying since we chose downward as positive, that means when it crosses that line, it is going downward, right? So do not be confused. We can see the graph, yes, is going all the way upward, but then in terms of the graph here, we are saying when it crosses this x-axis line, it is going downward. And then when it is below here, we are saying the motion is upward, right? So now let's understand what is going on. We know that the y-intercept here, so the y-intercept, the velocity that you'll be given here will be indicating the initial velocity of that object or of interest that we'll be talking about. And then the x-intercept here will be indicating the time taken to reach the maximum height. So now we know that the velocity at the maximum height is 0 meters per second. So now you can see that the velocity here, remember at this point we are saying the ball here will be at the maximum height, and then you can see that the velocity that corresponds with that is 0, right? So at the maximum height we say the velocity is 0. Then at this point, remember when the ball is now at maximum height, the direction that it needs to take is downward, right? So for this one, we'd have a case like this whereby we can have a person throwing an object upward from on top of the building, then throwing it upward, and then the ball reaches the maximum height and then it goes back down. So from the point where it is released up until the maximum height, that will be indicated by this part of the graph here. So we can see what is going on when the ball is projected upward. When the ball is projected upward to reach the maximum height, the velocity of the ball decreases. Remember, when you throw the ball upward, the kinetic energy needs to decrease. Also, the velocity will decrease up until it reaches the maximum height, where now the velocity will be 0 meters per second. So the idea is if I throw a ball at this point, maybe at a velocity of 10 meters per second upward, then as it goes, the velocity is decreasing up until it reaches a point where the velocity is 0, which is the maximum height. Then at that point, what happens? The ball is now coming back down. But then when it comes back down, it's gaining kinetic energy. So its EK increases as it goes down, right? So when the EK increases, also the velocity increases, which is indicated by this increase in the graph on the downward position, right, on the downward side. So above the x-axis, since now we took downward as positive. Now, what about if we took upward as positive? When we take upward as positive, we know that we now have to indicate this position above the x-axis as upward, and then the one that is below the x-axis will be downward. So what is going on? That is still the same scenario. The ball is thrown upward, but then as it is thrown upward, what happens? The velocity decreases. So don't be confused. This is not the part of the ball. This only indicates the velocity of the ball. So as the ball is going upward, what happens to its velocity? It decreases. The velocity decreases up until it reaches that maximum height where the velocity is 0 meters per second. Then after reaching that maximum height, what happens to the ball? It has no other direction but to go back down, right? So at this point, what is happening? After it reaches that maximum height, it continues in that direction, and then there it goes. So we have that they say the velocity at the end of the graph is the final velocity for the whole journey. So the velocity that you're gonna acquire there, that's the final velocity, right? So the final velocity will be indicated by the value that will be obtained here. And here the time here will be the time that was taken for the whole journey. So if the whole journey for the ball is 2.5 seconds, we want to indicate the 2.5 seconds there. And if it took it 0.5 seconds to reach the maximum height, from that position it was released, then we indicate the time to reach the maximum height here, right? So having all that, let's look at the scenarios that we have. So we have a scenario whereby a ball is thrown upward, it reaches the maximum height and hits the ground. So that is basically the scenario that I spoke about in that question, whereby you'd have something like this, This is a boy throwing a ball upward at a certain velocity, let's call it v, and then it reaches the maximum height. So at the maximum height, we know the velocity here will be 0 meters per second, and then it goes all the way down there. Let's say it reaches the ground at a velocity of 4v, so 4 times whatever the velocity that I have here. Because remember, as it goes down, its kinetic energy increases and also its velocity increases. So how would you indicate that in a velocity versus time graph? So this is how you have it. Let's say now our velocity here is v, right? And then it reaches that point. Then the velocity finally here will be indicated as, so we have our velocity finally going all the way, and then that's 4v. So you can also do that with values. So if I were to give you values, let's say now I say v is equals to 10 meters per second. So we'd say the ball is thrown at a speed of 10 meters per second. So we'd say the ball is now thrown at a velocity of 10 meters per second. So it will just be a matter of coming in, say 10 meters per second. And then obviously 4v would now be 40 meters per second, right? So you just indicate 40 and then you'd indicate 10 here, right? So that's how you'd have that. Okay, so now let's look at the scenarios. We have a ball is thrown upward, reaches the maximum height and hits the ground. So basically that's what we've been doing there. So here is on top of a building. Let's say maybe it's 40 meters above the ground. Then the boy here decides to throw the ball upward. So here is the ball thrown upward and then reaches the maximum height, passes that point of release, and then goes way down to hit the ground. So to indicate that, let's say let's make it a full question now. Let's say now they're saying the ball was released at a speed of 8 meters per second, and then let's say it reaches the maximum height at time, let's say 1.2 seconds. That's the time it took to reach that maximum height. Then when it goes back down, it hits the ground. Let's say it hits the ground at a velocity of, we can say it hits the ground at a final velocity of, let's say 20 meters per second. So how would we use all that information to draw our graph? So we'd have that. Remember, if we have this graph, we are simply indicating that we are taking our downward as positive. Why do we say so? Because we can see that our graph is an increasing function. So always know that if we have an increasing function like that, we took downward as positive. So that means our down is up here. So down is up here, downward, and then upward will be below here. So this would be upward. Now, what is our initial velocity? Our initial velocity, the ball was projected upward at 8 meters per second. But remember, projected upward, but we took downward as positive. So it needs to be negative. So now, being projected upward, it goes up, goes up, goes up until it reaches the maximum height. So it reaches the maximum height at time 1.2. So we indicate the time taken to reach the maximum height, right? And then we can see that it corresponds to that 0, whereby we know that the velocity at the maximum height is always 0. Now, after reaching that maximum height, where does the ball now go? It goes downward. As you can see, it now crosses that x-axis line. So now the ball is going downward. What is happening to the velocity? The velocity is increasing as it goes upward. It's increasing, increasing up until it reaches the ground, right? So let's say the total journey, took 5 seconds. So we're gonna indicate our 5 there. So if we say the whole journey took 5 seconds, and then let's say we said it reaches there at a speed of 20, right? So let's indicate our 20 there. So that's how you'd have your graph, right? So that's how you'd have your graph. You have your V initially, that's -8. You have the V finally, that's 20. And then you have the time taken to reach the maximum height, that's 1.2 seconds. And you have the time it takes for the ball to hit the ground. So this is the time taken for the ball to hit the ground, or the total time of the whole chain. Now let's have scenario number 2. They say a ball is dropped from on top of a building and it hits the ground. Now you can see the keyword here is dropped. So we know when they say dropped, that our initial velocity is 0. As you can see with the graph, remember the x-intercept, we said it indicates the initial velocity. So you can see that our initial velocity here is 0, right? So this ball is dropped. So this is a scenario whereby you have, let's say it's on top of a building. Again, let's use 40 meter high. But then instead of throwing it upward, the ball is just dropped like this. So if it's dropped, it goes like that. Then what is happening? We know that as the ball is dropped, the velocity increases, right? But then can you see this graph? What direction is positive here? So from this we can see that this is a decreasing function. So we know they took upward as positive, right? So upward is there and downward is down below here, right? As you can see that we don't have the graph above the x-axis. Why don't we have the graph above the x-axis? Because the ball never went up. The ball never went up, it just went down, right? So remember, took upward as positive but downward as negative. So the graph will be obtained below the x-axis because the ball is actually going down, right? So you'd have, if you took let's say if you took If you took downward as positive, the same graph, you'd have it like this. Have the graph like that, whereby now we'd say the upward will be down above the x-axis and the downward will be above the x-axis. So remember, also the graph, again, also the ball doesn't go upward, so it goes downward, so it is indicated there, because in this case we would have took downward as positive, so the graph will be increasing function. You'd see that it is above the x-axis where you see downward, right? Okay, so let's look at scenarios whereby we have the ball bouncing on the floor. So for those, we have two scenarios whereby we have an elastic collision or elastic bounces, and also inelastic bounces, right? So for elastic bounces, we know from the word elastic collision in momentum, we know that elastic collision, this is where the kinetic energy will be conserved. So there will be no loss of energy. So we expect here that the velocity that we'll be dealing with will not change, right? So now let's see, from looking at the graph, we can tell that we are given upward as positive. Why? Because this is a decreasing function, right? So we can see that this is a decreasing function. This indicated there upward as positive, and our A is negative. So pardon that mistake, that's negative 9.8 meters per second square, right? So now let's check and understand what is going on. Let's interpret this graph. So having to interpret this graph, let's draw what's probably going on here. So this is the case whereby we have a ball that is thrown maybe from on top of a building. It goes all the way down, hits the ground, and then when it hits the ground, it bounces off and reaches that same height in which it was released, because remember, this is elastic collisions, right? So if it's elastic collisions, we say that when the ball bounces, it must reach that maximum height in which it was released. Remember, we are saying there is no loss of kinetic energy. So the same energy that was here at this point must be the same energy that takes the ball from the ground all the way up to the point which it was released, right? So we see that that's a situation, and then again there's a second bounce. When it bounces off again, it goes where? To the maximum height. So this time when it bounces and then leave it at the maximum height. So this is what is happening here. As you can see, the ball is dropped, right? So this ball was not projected, it was dropped. You can see the initial velocity is 0. Then the ball is falling. So we know as the ball is going down, what is happening to the velocity? It is increasing, right? But then remember, increasing in the negative direction. Why? Because we took upward as positive. So we know when we take upward as positive, the up found here above the x-axis, and the down is actually below the x-axis. Now we know, having this, where will be our ground? The ground is always downward, right? So you can never find your ground upward, right? And the ground is here. So this point will indicate the ground, right? So that line indicates the ground. Let's say now this is it. The ball is thrown at, is dropped at that 0, and then it keeps falling. So we know as it's falling, what happens to the velocity? It increases. Let's say now it reaches the ground at a velocity of 10, right? Let's say by the time it reaches the ground, its velocity has increased to 10 meters per second. So we know it's negative, right? Remember, we took upward as positive, so negative 10 is going downward. That's why it's negative like that. Then when it strikes the ground, and then changes. When it strikes the ground, it changes the direction. It's now going upward. Hence we now have our graph starting upward there, right? to indicate that after the bounce there was that change in direction, but the velocity in which it hit the ground with, that 10 meters per second, will be the same velocity in which it leaves the ground with or bounces off the ground with. Why? Because this is elastic collision and we are saying there is no loss of kinetic energy, meaning also the velocities will be equal, right? The same velocity it hits the ground with will be the same velocity it leaves the ground with. Now after bouncing off, we know that it rises, goes to the maximum height where the velocity is now 0, right? But then now again it crosses the x-axis line, meaning it's now going down. So this is a scenario whereby it's now going down. After reaching the maximum height here, it goes down. As it goes down, what is happening to the velocity? It's increasing up until it reaches the ground again. When it reaches the ground, it does what? It bounces up. So when it reaches the ground, it does what? It bounces up, right? So we can see it bouncing up like that. And then from that point, after bouncing up, so that's the bounce. It goes all the way up, so it's rising up until it reaches the maximum height, right? So up until it reaches the maximum height, and that's the whole chain. Now let's check the same scenario, but now if we took downward as positive. If we took downward as positive, that means here we'd have our downward, and then below here we'd have our upward, right? Now where is the ground this time? The ground will be here, right? The ground will be here. Remember, the ground is always in the downward direction. So that's the ground, ground. So let's indicate ground. So what is happening now? Again, it's the same scenario. The ball was dropped, and then after being dropped, it goes where? Downward, right? So as it goes downward, what is happening to the velocity? The velocity increases until the ground, until the ball strikes the ground, and then after striking the ground, it bounces and then takes off, goes to where? The maximum height at sea. From the maximum height, what does it do? It falls. So here there is falling. So in this case, you'd have your falling here. So the graph is falling here, and then it's rising where? It's rising here. So our rising is here, and then goes to the maximum height, starts falling, and then it bounces. So these ones will indicate our bounces, and then our bounces, then at this point, what is it doing? So it's rising, because after hitting the ground, it hits the ground, bounce, and starts to rise again. So that will be the scenario if you took downward as positive. Now, why do we say the collisions are elastic? We say the velocity it reaches the ground with is the one it bounces off the ground with, right? So because the velocity in which it hits the ground with, the -10, is the same velocity that it takes off the ground with, that's why we say it's elastic. There is no loss of energy. Then again, we say the heights of the graphs are equal. As you can see there, the heights of the graph from B to D, you can actually put a straight line there. then there is no gap in between the x-axis of the graph, indicating that there is no significant contact time with the ground. As you can see here, the graph is just straight. The broken lines are straight like that to indicate that there is no contact time with the ground. Okay, so now let's look at an inelastic collision. So with this one, again, we can see the velocity versus time graph here that we've been provided with is the one whereby we took downward as positive. Why? Because we can see that this is an increasing function. So immediately we just indicate that downward is above the x-axis. So this is downwards, and then below we'll have upwards, right? Below will have upwards. So as the graph is being projected, so we can see the graph, the board is being projected, meant to say, as the board is being projected upward, is being projected downward, because remember downward is above. So as when the graph is still above the x-axis, that indicates that our ball is still moving downward. So we can see that the board is being projected downward. So this will be a scenario whereby you have something like this. Let's say it's on top of a building, decides to project this ball downward at 2 meters per second. Now we know it will reach the ground at a velocity that is greater than that. So reaches the ground at 9.6 meters per second, right? But then this time it is in contact with the ground for some time, and then leaves off the ground at negative 8 meters per second. So the negative 8 indicates that now it's going upward, and then reaches the maximum height t, whereby we can see that the velocity there is 0. Then after reaching that maximum height, it goes back down. So we can see that after t, it crosses the x-axis, which is now going where? Downward, right? So it's going back down there, like that. So let's check what is going on here. So we can see here projected at 2 meters per second, reaches the ground. Remember, the ground is always on the side whereby we have downward. So reaches the ground at 9.6 meters per second. But then what happens? You can see here that we no longer have that perfect straight line. This line is now slanted, right? So to indicate that there is now contact time with the ground, it's no longer as straight as the ones for elastic collisions. So you can actually see the difference here between the two. So with these ones, you can see that this is a straight line, and then but here you can see that this is not a perfect straight line. This is slanted, a bit slanted, so it's not going vertically, it's more like diagonal, right? So they're both straight lines, but then that one is vertical, but this one is a little bit diagonal, right? Then we have that. So it hits the ground. When it hits the ground, check the velocity in which it leaves the ground with. So remember, this one is the bounce. So here what was happening, this is the falling. So it's falling, and then here this is the bounce, right? But then when it bounces off at a velocity that is now lower than the velocity it strikes the ground with. So it strikes the ground at a velocity of 9.6 meters per second, but now it leaves at 8 meters per second. Why was there a decrease in velocity? Because now we are saying there was that loss of kinetic energy. So now the ball lost its energy to the frictional forces on the ground. Hence now when it bounces off at a lower velocity. So it bounces off, it reaches the maximum height. But then look again, when it now goes back down, you can see that the velocity in which it reaches the ground with will no longer be the same again. So it will be lower now, because what is happening, it's losing its kinetic energy. So you can see here it's no longer going back to that height, it's now at that velocity there. So we know if it left at -8, it will hit back the ground at +8 there. So if you were to extend that, you'd have 8 there, right? So you can see that by looking at the values here, you can tell that this ball cannot bounce back to that to that initial height in which it was released. Now, why do we say this collision is inelastic? So we say the velocity the ball bounces off the ground with is lower than the one it reaches the ground with, as a result of a loss of kinetic energy when it is in contact with the ground. The ball will reach a lower maximum height every time it bounces off the ground. Then we can see there is a gap between the x-axis of the graph. So this is why we say this collision is inelastic, for those reasons. Then let's look at position versus time graph. So let's understand this. The xi here is indicating the initial height from which the ball is thrown. The xf is indicating the final height or displacement covered by the ball. And then the hm is the maximum height reached by the ball. So here, this would be the maximum height. So the value that will correspond to that peak level there would be your maximum height. And then Tm is the time taken to reach the maximum height, which we can see here. This is forming the, if you use the properties of the parabola, you can see that that time is indicating the axis of symmetry, right? That will be the time taken to reach the ground. So that will be the time taken to reach the maximum height, right? And then TF, that will be the total time taken for the whole journey, right? So all the way from when the ball is released and then it goes to the maximum height and back to the ground, right? So it's simple to draw position versus time graph because you simply look at the trajectory of the ball. You just look at the path that the ball takes, right? And then you just try to draw it into your position versus time graph. Right? So with this one, we have an inelastic collision. With an inelastic collision, and number one, you can see that we are dropping this ball from a position of 2 meters. Then when we drop this ball from that height, 2 meters, what happens here? So we project that ball there, it's released, and then it reaches what? It reaches the ground here. When it reaches the ground, what happens? There is a gap there in between the x-axis, as you can see. So we have that gap in between the x-axis to indicate that there is now contact time with the ground, meaning that the ball is now losing kinetic energy to the ground, right? Or to the frictional forces, right? So we indicate that, so that gap is indicating the contact time with the ground. That gap is indicating the contact time with the ground, whereby this is where we have the loss of kinetic energy. This is where we have loss of kinetic energy. And this is where now our velocity will decrease. Now, since we have that loss of kinetic energy, you see now after the bounce, the ball will no longer reach the initial maximum height. So it will now have a lower maximum height. And then it goes back to the ground, bounces again, and reaches a lower maximum height again, right? So why do we say these are inelastic collision? We say the ball reaches a lower maximum height after every bounce, and there are gaps in between the x-axis of the graph indicating a contact time with the ground, and then due to loss of kinetic energy when the ball hits the ground, right? So those gaps are due to a loss of kinetic energy when the ball hits the ground. Okay, so now let's look at the scenarios. They say ball is thrown vertically upward from on top of the building, then it hits the ground. So we can see there that we are given a position versus time graph, and then we took our upward as positive. So the way to see it is if we take upward as positive, our position versus time graph will be above the x-axis. So this is it here. So this will be our upward, and down here will be our downward, right? So if we take a positive, upward as positive, our graph will just be above the x-axis, right? Then indicating this scenario, let's have something like this. Let's say for this one, we'd have a scenario whereby a ball from on top of a building, let's say the building is 50-meter above the ground. The ball is 50-meter above the ground on top of this building. The ball is being projected upward and then goes back down. So with this, it's the ground. It's the ground, right? So this is the ground. So with this, with your position versus time graph, it's easy to draw this because it's just a matter of cutting and pasting your trajectory of the ball. So this is the part that has been taken by the ball. You just simply take it as it is, paste it into your graph here. Especially if you took upward as positive, it becomes very easy to draw. So you paste it here. So let's say here now at this point we'll be indicating our 50-meter, and we are simply making the ground the reference point, so that zero line will now be the ground, right? So if they say take the ground as reference point, so this is being thrown from this height 50-meter above the ground, and then it goes up. Let's say when it goes up, it reaches a maximum height of 55. Let's say it reaches a maximum height of 55, then above the ground, so it reaches a maximum height of 5-meter if you take it from if you reference from on top of the building, because from 50 to 55 that's 5, but then in reference to the ground, that's 55-meter above the ground, right? Then let's say it took about 2 seconds to cover the distance, so we'll indicate the time taken to reach the maximum height will be 2 seconds here, 2 seconds. Then let's say the whole journey took about 6 seconds. So that's how you'd have that. That's how you'd have that. Then if you are looking at the same scenario, but now you took downward as positive, it's just a matter of taking this graph, and if you apply your maths, you just reflect it along the x-axis line. So you reflect it along the x-axis. Then this is how you'd have your graph. Again here, this time you'd have your negative 50 here, and then at this point what would you have? So at this point you'd have your negative 55, right? Then the time taken to reach that, that's we said, what is the time taken to reach the maximum height? 2 seconds. So 2 seconds being the time to reach the maximum height, and 6 seconds being the time for the total journey, right? So, and that's how you would have your position versus time. And never forget to label also. So this side here you have position, and then it's always given in task. And this side here you have time, which is always indicated in seconds. So you have position versus time. Then let's look at another scenario. Let's say now the ball is dropped from on top of a building and it hits the ground. Again, if we take upward as positive, this ball is dropped. So if the ball is dropped from on top of a building, the trajectory is that it will go like that, right? So this is how you show it. You just show it in that graph. Let's say again the height which it was thrown 50-meter. So you just indicate that 50 meter, and then let's say it took about 2.5 seconds to hit the ground. So you just come here and indicate that 2.5. That is the time that it took the ball to hit the ground. So remember, the ground is our reference point, right? And that's how you'd indicate that. Again, having the same scenario, but now you take downward as positive. That means here you'd have negative 50. So again, it's just a matter of reflecting it along the x-axis, and then again here you have 2.5, right? 2.5. Now let's look at the scenario whereby we have bounces. So again here we have two scenarios: the elastic bounces or collision, and also the inelastic bounces. So with this one, it's quite easy to see. The elastic bounces, obviously you'd see that your ball will reach the same height that it reached before, right? So if we're to throw this ball upward, it goes upward, reaches a maximum height of 81.63, and then it goes back down to hit the ground. When it hits the ground, it also goes back up, reaches that maximum height. Let's say maximum height that it reached at first, it will reach that. So we say the heights of the graph will be equal, it will reach the same maximum height. So that indicates the elastic collision. And also again, you will note that there is no gap in between the x-axis of this graph to indicate that there is no significant contact time with the ground. So that means there was no loss of kinetic energy. So that is it. Why do we say the collision is elastic? We say the ball reaches the same height after the bounce, and then there is no gap in between the x-axis, which indicates that there is no significant contact time with the ground. Then we have obviously the last part of the lesson, which is looking at acceleration versus time graphs, which are the easiest to draw because all you just do here is to know where to put your 9.8. Then for this one, let's say we are taking our upward as positive. So for upward as positive, we know that our acceleration is negative 9.8 meters per second square. So drawing an acceleration versus time graph for this one, have it like that. So you'd have it like that, and then since we know that we are taking our upward as positive and our acceleration is negative, therefore our acceleration will be down below here, right? And then that will give you negative 9.8. Then it's just a matter of indicating that here you have time in seconds, and then here you have your acceleration in meters per second square, right? And that's your acceleration versus time graph if you took upward as positive. What if you took a downward as positive? So for downward as positive, you know that your acceleration is now positive 9.8. That means your graph will be above. Then you have 9.8, and then here that's your 0. That's your 0 here. And then this is when you took, let's indicate, this is when you took downward as positive, because our acceleration is positive 9.8 meters per second square. So this is how you'll have it. You'll have that 9.8 being above the x-axis. Remember, it's positive. So this is the graph of acceleration versus time when you take upward as positive, and this is the graph for acceleration versus time when you take downward as positive, right? And that's it for the lesson. Ra.